Hello all, welcome to part 4 of the SLAE course, and in this video we will finally look at a Hello World program and how you can code it up in assembly. Now before we move into all of that, one needs to understand the different instruction sets available for IA32. So you first have the general purpose instruction set, which typically uses the general purpose registers and the E flags. Then you have the x87 FPU instruction set, which is anything you want to do with floating point numbers. You could basically use this instruction set. After that, you have the extensions, which include MMX, SSE, SSE2, SSE3, SSE4, and anything Intel decides to come out with later as an extension. Now, we've seen in the very first video that to go ahead and create the final machine language code, we need to take an assembly file and use an assembler linker combination to convert it into machine code which the CPU can understand. Now, this is done using NASM and LD in our case. NASM is an assembler called the net-wide assembler. It's free, open source. You can download it from the link below. I've already shown you how to install NASM on Ubuntu in an earlier video, so you should already have it. And LD is basically the linker which links the object files, shared libraries, anything you would need to go ahead and finally create the executable. The executable which we will create is in the ELF format, which is the most common format on Linux-based systems. Okay, so in order to create a Hello World program, what exactly do we need to do? So as I mentioned to you previously in the last video, all the program code needs to be inside what is called a text section. So let me actually go ahead and let's type all of this together, right? So let's create a file called hello world.asm, right? And I'm going to use Vim. You can use any text editor you are comfortable with on Linux, such as Pico or anything else for that matter. Now, in order to go ahead and enter a comment, we can basically go ahead and use this character and then say hello world.asm, right? You can type in your name, author, and now we come to the main meat of the program. Now, as I mentioned, the very first thing we want to do is mention a text section, and the way you can do that is by entering section, and then you can actually mention that this is the text section. Fantastic. Let's go back to the slides. Now, in the Hello World program, as you imagine, we want to mention the string Hello World somewhere, and this would have to be in the data section where all the initialized data is put in. So now let's go back and mention the data section. Let's do it down below. So we say section, and then we can actually go ahead and say .data. Now inside the data section, you want to mention the hello world string. So let's go back to our program, and here is where I introduce you to something called a label, right? So what we are going to do is the message we want to print, hit a tab, you could ignore that if you like, message colon, and now we want to go ahead and basically put our string hello world inside the data section. Now to do that, we could actually use something called db or define byte, with which we can define a series of bytes or even an individual byte, and this is something NASM understands, right? and we can actually say after that hello world with our exclamation, and here goes, right? So this is how we are going to go ahead and define hello world string inside the data section. Note that this is inside the data section, and we are identifying the hello world string with the label message, which we will later on use in the program. Let's go back to our slides. Now that we have defined all of these sections, the next logical step, as you can imagine, we have a text section which can contain procedures, which can contain a lot of code. So it is important to be able to tell the linker where the entry point of the program is actually going to be. And this is where we are going to identify the entry point using the _start identifier. So let me actually go back here, and I'm going to go inside the text section and basically put in _start, which kind of identifies where the program entry point is going to be. And I would need to go ahead and mention this up on top as well, which actually would say we use the global identifier, and this basically says, hey, we are going to use _start as the entry point, right? Fantastic. Now let's go ahead, come back in here, and now comes in the next part where we need to figure out how to print to screen and how to exit gracefully, right? So we want to print hello world to the screen. Okay, now this is where we need to understand a little bit more about how all of this works. Now, as far as printing to screen is concerned, you could manage somehow to use all the low-level features of interfacing with hardware and all of that. But as you can imagine, that is not something which you would like to do. Instead, you would like to leverage the operating system for more complicated tasks. And when I mean more complicated tasks, it would be, for example, writing to disk, printing on screen, interfacing with certain devices and things like that, where writing code from scratch could really be very, very cumbersome, right? This is where system calls come in. Now, system calls provide a very simple interface for user space programs to request the kernel to do complicated tasks for them. Now, how do system calls work, right? Now, a user space program calls a system call, and once that is done, so as an example, one way of invoking system calls is to generate an interrupt 0x80. Once that interrupt is generated, the CPU will go ahead and check the interrupt handler table and invoke the system call handler. Now, once this is done, the system call handler basically is a kernel mode program. And this system call handler goes ahead and figures out the specific system call routine we are interested in. So as an example, if you want to write to the screen, there is a specific system call for that. If you would like to go ahead and read something from input, that's basically a separate system call, right? Now, where are all of these system calls mentioned? I'll come to that in just a bit. But before that, there are multiple ways by which you can invoke these system calls in user space programs. On IA32, you can do this by using interrupt 0x80 or the sysenter instruction. It's important to note here that modern implementations typically use something called VDSO, or Virtual Dynamic Shared Object, which is a more efficient way of doing system calls. Now, how VDSO works and all of that is probably beyond what I could cover in this course, simply because it requires you to understand more about how the kernel functions, how the loader works, and a bunch of other things. However, if you're interested, you could refer to the link below and understand how system call is actually implemented in the kernel. Now, from our perspective, which is pure security, shell coding and all of that, we would almost exclusively look at interrupt 0x80 for whatever we do with respect to system calls. Okay, so we said that there are so many system calls which may be available. The next logical question arises, where are these system calls defined, right? So let me open up a new terminal. And I'm going to open up the file user include i386 Linux GNU. And remember, if you use a different system, the location would be different. And then after that, you have a bunch of files in here. The one we are interested in is the 32-bit one, which is unisted_32.h. And this mentions the full list of system calls which are available to you, right? There are many system calls, as you can clearly see. System calls to create directories, to change directories, to make nodes, to unlink files, to go ahead, open, read, write, and whatnot, to restart the system, to exit a program, to fork a new process. Practically all the low-level stuff which you would want the operating system to do is all mentioned in the form of system calls. And this is of huge importance to us. Okay, let's come back. Let's go back to the slides. Now, we go back to what we really wanted to do, which is print to the screen and then exit the program gracefully, right? And this is where we need to use appropriate system calls to do both of this. Now, to write to a screen, we basically want to use the write system call, right? And the write system call is basically identified with the syscall number 4, and you would actually have a wrapper on it, which you can figure out via the documentation using man to write. And if you read through the documentation, you can invoke write. The first input is actually going to be a file descriptor. The second input is going to be the buffer, which actually contains what you want to write into this file. And then finally is the length of what you want to write, right? Now, in our case, we want to write to std out. Now, for any program, by default, std in, or the input, is mapped to file descriptor 0, std out is mapped to 1, and std error is mapped to 2. So in our case, the value of fd is going to be 1. Now, buffer or buff actually would be pointing to the hello world string which we have. And finally, count is nothing but the length of the hello world string, right? Fantastic. Let's go back to the slides. Similarly, exit just requires us to give an exit status. Typically, the value 0 is used to indicate that the program exited without any problems. If you give a non-zero value, that may have an indication that the program had certain issues while exiting. Now, the question arises, we have all of these inputs which need to be fed into the system call, right? How do you pass all of these inputs before invoking a system call? Now, this is where for IA32, you are going to go ahead and pass these via registers. Now, the EAX register must contain the system call number. If you remember, we found out that for write, the value of this number is 4. EBX, ECX, EDX, ESI, and EDI would contain the first, second, third, fourth, and fifth argument, depending on the number of arguments, right? If you have more than that, the ideal way would be to pass them in the form of structures. Now, once the system call returns, because every system call would typically have some sort of a return value, the return value is pretty much put always inside the EAX register. This is important if you would like to use the return value of the system call further in the program. Now, to elaborate on that, basically EAX register would contain the system call number. EBX would basically contain what intfd should be, and as we figured, that would be std out, and the value for that is actually 1. After that, ECX would actually point to the hello world string, and EDX would have to contain the length of the hello world string which we want to print. So let's go ahead and set all of this up in our little program here. So what we mentioned was that the EAX register would have to contain the syscall number, and what we located that for write the value is 4. So move EAX the value 4. Right, you could also mention 0x4 in hex, but remember, either use hex or use decimal, don't mix up both. So let's just use hex. Now then we said EBX basically would contain std out, which is 1, so EBX would be 1, and the move instruction, we'll take this up a little later in more detail, is responsible for moving data into registers, between registers and memory location and all of that. So the way move works is, this is the destination and this is the source. So move EAX, 0x4 moves the value 4 into the EAX register. Move EBX 0x1 moves the value 1 into the EBX register, right? So on and so forth. Now the third thing which we said is ECX would actually have to contain the pointer pointing to the hello world instruction. Now the interesting part is we can reference the hello world string with just the message label. So move ECX would actually message would actually move the address of the hello world string into ECX. After that, we want to move the length of the hello world instruction, which we can do basically as a first iteration by counting it, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. This is one way of doing it, and you could put in the value basically 12 in here. Alternately, there's a quick shortcut which you can actually use, which NASM understands. You can say message length equals $ minus message and this would basically have mlen in here. Right, so this automatically computes the message length for us. Awesome. And then after all of this, as I mentioned, we need to go ahead and issue the system call, which is done by issuing via interrupt 0x80. So this is basically going to go ahead and print hello world on the screen. Now the next step is actually to exit the program gracefully. Exit the program gracefully. And kind of go back here, the call to exit. So the first thing is to find the system call number for exit, and then to find the status code which we want to return inside EBX. So if we go back here, exit basically is system call number 1, so it should actually mean move EAX 0x1, and then move EBX. Let's say we want to return the value 5, and then we basically enter 0x80 to issue the syscall, right? So this is how we are able to now create a very simple program. Now let's go ahead and assemble and link this. So let's use NASM. The -f option is basically the executable format which you want to create. In our case, it's ELF32. And then basically we mention the output file, which would be hello world.o, the object file, and this is the input file. And basically if we kind of go ahead and look at the instruction here, I think I made one little mistake. You have EQU for equal. There you go. So now basically you notice that we have an object file hello world.o, and what we need to do next is basically link this into an executable ELF format. So you're going to say hello world, and here is the object file, right? So now we have a hello world executable inside the same directory. Let's run it, and it printed hello world. Fantastic. And if you want to look at the return value of the program, you could just do an echo $? And if you notice, the return value was 5, which is exactly what we had given in the program, right? Chose the value 5. Awesome. So this is how we can create a very simple assembly language program to print hello world on IA32 Linux. And pretty much this whole format of writing an application file is exactly what we'll use in later videos as well. Now comes the exercise, right? Now we went ahead and created this hello world program, and the program kind of executed and we were able to see the output. However, what about analyzing and visualizing all those micro instructions such as move EAX, 0, move EBX1 and things like that? How do we go ahead and look at all of that at a microscopic level? This is where GDB comes in, and the exercise associated with this video is that use GDB to step through the hello world program, observe the CPU registers, see how data is being transferred, look at memory locations, and a bunch of other things, right? So that's all for this video. Thank you.